So the color that you see is not what's being absorbed, it's being what's reflected. So if you can, a lot of times, if you know the wavelength of what you're actually seeing, the wavelength of what is being absorbed is going to be the opposite of it, in a sense, like opposite color range. It is possible to measure the amount of light absorbed by using a spectrophotometer. That's why it's called the Spec 20, a spectrophotometer. So basically, spectrum photo reader, right? Like your speedometer measures your speed. This measures the spectrum light meter. So spectrophotometers in general contain a light source. This is just a simple bulb. It has a diffracting gradient, basically like those glasses. It allows you to sit there and only let certain wavelengths go through. So it separates lights into different wavelengths, a sample holder, which you saw, and a detector that basically detects the amount of light that passes. The amount or percent transmittance is the amount of light that gets through. The absorbance can be found by taking the negative, oops, I can't highlight it, taking the negative log of that transmittance. Luckily for us, the actual machine does that for us, right? We can press a button and it will give us the absorbance. So the absorbance itself, there is an equation called Beer's law, and it is this: absorbance equals the what's called the absorptivity multiplied by the path length times the concentration, and that's what gives you the absorbance. All our really major concern is we don't care about the path length or the absorptivity for this, because we are using the same substance over and over, and we are basing our graph off of concentration to absorbance. Easy enough. So that brings us to our laboratory for tomorrow. I'll bring that up and share that. Those of you that I will print out copies of this for those of you that are coming to do these labs themselves. But that lab is here, and you can see there is some background here for it. We have simplified the equation to be absorbency equals K, and we don't really care about that K because we are just basically doing a proportionality. So it's good. Then brackets. Have we talked about brackets meaning concentration in this class yet? Oh, this is a first then. If you have brackets around a formula, that means concentration. So that's why it's saying brackets around that. That is the concentration of this formula. Actually, were you going to say something? Do I have my volume down or something?
No, I wasn't going to say anything.
Cool. So if the absorbance, blah, 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 I don't think that's important. Keep in mind, you do want to make sure that your graph goes through the zero, the origin, because there will be zero absorption when the molar concentration is zero. You have made the stock solution, so I'm hoping that you did a good job on that.
Mr. Jackson, a quick question actually. For the graph, you said we can either do it like online, like Google Sheets, or like handmade.
Yeah, either way.
Okay.
And basically, this is the thing. You're going to find the maximum absorbing wavelength tomorrow. So tomorrow's kind of low stress. It's going to give you a little bit of time to, get your fingers on the machine and be able to sit there and look at the cuvette and stuff and see all that. And then high stress is going to be Friday. So we're going to pump you into the weekend with a little bit of high stress. I don't think, unless we have time tomorrow, maybe we use pipettes and pipette pumps, but I'm thinking we just use graduated cylinders. I don't know if it's necessary. It would be nice, I guess, to let you guys touch the pipettes and just have another instrument that you can use. I'll think about it. So that basically, Friday, you have to prepare several dilutions. So you want to make sure you have that math done when you come in Friday. Then you use the graph that you produce tomorrow to find the best maximum absorbance. So tomorrow will look like this, determining the maximum wavelength. You start at 400 and you basically zero out your instrument, have a blank to give 100% transmittance, and then you just stick in your stock solution that you made, a natural cuvette with the stock solution you made. And then you basically remove that, increase the wavelength by 20, and you do it again. And then you increase the wavelength by 20 and you do it again. You want to try to get from 400 to 640, but some of these machines won't let you go past 620. That's fine. Anytime you feel resistance to that machine, don't force it. You'll break it. And then you basically graph absorbency to wavelength on the X, because the absorbency is, what's the word I want? This is in the wavelength is independent of the absorbency, but the absorbency is dependent of the wavelength. And basically you'll get a graph like this. You want to find the wavelength that gives the most absorbance. This is the highest up here. And then you will use that absorbance for Friday. You will make 5 milliliters of each of these solutions. 5 milliliters in 0, 4 and 1, 3 and 2, 2 and 3, 1 and 4. And then you will calculate, and this is the data sheet for tomorrow's lab. And as I said, I'll have that printed out for you. You will calculate the molarities of these solutions where you have 5 and 1, 4 and 5 and 0, 4 and 1, 3 and 2. You calculate the molarities of those. And that will allow you to make your graph, absorbance to the molarities that you calculated, including 0.00. Then Friday, you will take 3 unknowns and you will plop them in there and get their absorbance and determine their unknowns using the graph. Questions there?
In our graph, do we have, so basically making 2 different graphs?
Yeah, you're making 2 graphs, that's true.
And then for the unknown solutions, in our final graph, do we have to include the unknown solutions in our graph, or is that just
You're
extrapolation?
going to use the graph to find them, yes.
Okay.
Let me see if it says make a small mark on your graph so that I know you didn't just do a visual estimate. So yeah, it looks like you do make a small mark on your graph.
Okay.
For those unknowns. So, all right, any questions about the review?
I have a quick question on like the multiple choice for number 2. When it says like they have a certain amount of grams of like solute per liter, it's referring to the liter of solution, correct?
Yes.
Okay, thank you.
Any others? That's all I got today then. If you need to stick around or whatnot, if not, I guess I'm gonna go make him and Gage's day happy and go splosh around in the creek with the Abe's kids. But if you do have questions, by all means, stick around. Have a great day.
Can you go over how to do number 4 on page 22?
Yeah. I'm surprised there aren't more questions, right? Test Monday. Let's take a look at it. That's all the way to Monday. We're not thinking that far ahead. This one right here? Yep, okay. So we're dissolving NaCl. So that means that we're going to have 2 particles for 2 moles of particles for every 1 mole of substance. We are in a 1.00 kilogram of water. The vapor pressure of the pure water is 23.8. We need to determine the vapor pressure of the solution. So the first thing we want to do is change from kilograms of water to moles of water. So that's 1,000 kilograms. I'm sorry, that's 1,000 grams in 1 kilogram. Every 18.02 grams is 1 mole. I should be able to do this in my head, but 1,000 divided by 18.02.
The answer is about 55.4938.
So that's how many moles of water we have. So that's going to go on the top and bottom, because that's what we want to find the mole fraction of the actual solvent. Yes. To this, we have 2 moles for every 1 mole of substance. We need to find how many moles 150 grams of NaCl is. You know the molar mass of sodium chloride? Is it 58.44? (150 divided by 58.44).
The answer is about 2.5667.
So that's how many moles of NaCl we have. Two times 2.5667 plus 55.49.
It's 60.6234.
55.49 divided by 60.62.
It's about 0.9153.
So that's basically the mole fraction right there. We're going to take and we're going to multiply that by the original tour. 0.915 times 23.8.
The answer is 21.777.
So that gives us 21.777, which will round up to 21.8.
Why did you put the 2 in front of the moles of NaCl?
So NaCl completely dissolves, producing Na plus and Cl minus ions. The mole fraction is the mole of the solvent over the entirety mole of the mole number of the solution. So for every 1 mole of 2.567 moles of salt, we get 2 of those though. It's the I factor. You remember the Van Hoff factor, the I? That's what that 2 is. And because
Oh, okay.
sodium chloride dissociates, yeah. It's not directly seen in the equation, is it?
I don't have it written down. No.
But what you could do is this. The X of the solvent equals, my stupid pen's running out. Give me 1 second. If you have this written somewhere, that may remind you to do that. Does that make sense? Any other questions?
Yes. Did you get my email about my submission of that lab?
Yeah, that's what I was talking about at the beginning. It looks like I have some things to grade.
Oh,
Yeah.
it wasn't there.
I'll hopefully get them in before the week's over.
Okay, cool. Thank you.
You're welcome.
So for the unknown solutions, to find the absorbance, we're using the graph that we already made.
Yes. And we haven't made it yet though, right?
Yeah.
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 You'll use the graph. Yeah. You won't need that on the day of it. You'll be able to have that. Like all you need to get is the absorbance, and then you can use the graph after you make it. Yes.
Okay. Thank you.
You're welcome.
My last question is on page 22, number 5. Can you explain
Boiling
what
point
that
goes
means?
up. Freezing point goes down, and osmotic pressure. Osmotic pressure also goes up, right?
So why is that?
remember we said like putting the salt on the outside of this of the slug, all the water goes out because there's not enough pressure on the outside of the slug to keep it from going out.
Yeah.
Yeah, if the earth had a higher atmospheric pressure, then that may not kill the slug. But that water wants to move out because there's not enough pressure to keep it in.
Okay, I think I'm just confused about like what non-volatile versus like volatile means because I'm
Right. So volatile, like even water in our atmosphere is kind of volatile. It will evaporate by itself, right? It'll vaporize. But something that's more volatile, it will do it much quicker.
okay, and that's volatile.
Basically, all volatile means is it can vaporize.
Okay.
Like you know how like gasoline is volatile. You know
Yeah.
how you can see the fumes of it. That's all it means. It's not a word to get stuck on really. It just means like, you know, like when we talk about it, like we think of it like as explosive or something like that. But basically, it means it vaporizes. Versus
Okay.
salt. Salt doesn't vaporize, does it?
Mm.
Yeah.
Okay. Okay. I'll just try and memorize that.
Yeah, it's a weird one. I missed the vapor pressure, but that goes down. So let's think about it this way, maybe. If you have something here, you know that there is atmospheric pressure pushing down on it, right?
Yeah.
Yeah. So if there is particles in here, the volatile or the solvent, whatever you want to call it, is going to be attracted and bundled up with those particles. So it won't take as much pressure pushing down on them to keep that in liquid state.
Because the non-volatile doesn't evaporate as easily.
Basically because it's attracted to the particles that make up the solvent as well. So
Okay, so would this be like an example of like salt and water?
it could be,
Okay.
yeah.
Okay, that makes more sense. All right.
Cool.
Okay. Thank you.
You're welcome. Have a great day. Claudia, are you okay?